Good evening, sir. My name is Yatla Ajay Kumar, wearing roll number 24BQ1A04I8, studying in ECEC section in second year VVATU college. Today I am here to tell about the seminar topic about power spectral density from Unit 5. The key components or the essentials required to the seminar topic is about the introduction of the power spectral density, and next the key ideas from the power spectral density and its relation about with the Fourier transform and the autocorrelation function, and next about its properties. There are mainly 4 or 5 properties of the power spectral density, and finally I will end with the applications about the power spectral density. Next, first of all we have to tell about the introduction about the power spectral density. The power spectral density is PSD is a fundamental concept in signal processing that described how the power of a signal is distributed across different frequency components. Here the power spectral density PSD is mainly based on the signal processing. It tells us about the how the power of a signal is distributed across different frequency components. And next, instead of looking at how a signal changes over time, the PSD helps us understand how much power is present at each frequency, offering a frequency domain view of the signal. The power spectral density mainly gives us about the change the signal changes over the time. Next, the key ideas about the power spectral density. Mainly the power spectral density is mainly based on two components. One is power and another is frequency. PSD shows us how much power or energy per unit frequency is contained in a signal at each frequency. PSD tells us how the power or energy or anything per unit frequency is obtained in a signal at each frequency. Next, it is useful for random or noisy signals. When signals are too complex or random, like it have noise or any other disturbances in the signals, analyzing them in time domain is very difficult to us. Then PSD provides a clear picture of their frequency characteristics. So we use the power spectral density to reduce the complexity of the random, and random means like it have noise or any something disturbances in the main message signal. We have to reduce that noise or any disturbances by using a power spectral density. Next, how we computed the power spectral density from Fourier transform. Mainly power spectral density is estimated using the Fourier transform of a signal methods like the periodogram, Veitch's method, and autoregressive models are commonly used. To compute the power spectral density from the Fourier transform, we use here the mentioned methods are mainly 3. One is the periodogram, and second is Welch's method, and third is autoregressive models. These methods are used to analyze the power spectral density from the Fourier transforms. Next, the PSD is also defined as the Fourier transform of the autocorrelation function. When we do the Fourier transform of the autocorrelation function, we will get power spectral density. This is the formula for that power spectral density from the autocorrelation function of the Fourier transform of the autocorrelation function. The formula is Sx of j fk equals to limit minus infinity to infinity Rx of j transpose into k into exponential of minus j 2 pi ft dt. This is also known as Wiener-Khinchin theorem. This formula is also known as Wiener-Khinchin theorem. Next, the interpretation about that formula is PSD gives us mainly the power per unit frequency. Example, power means watt and frequency means Hz. This is the unit of power spectral density. Units for power spectral density. Next, power spectral density also shows us how much of the signal's variance is associated with each frequency band. Next, Next we will go through the properties of the Bohr spectral density. First property is about non-negativity. The non-negativity theorem is Sxx of j f of k always greater than or equal to Sxx of j into f of k always greater than or equal to 0. It means a PSD represents power which cannot be negative. We know that power should not be negative. Power always should be positive, like mainly starting from 0, 1, 2, 3. That how they, in the similar manner, power spectral density also represents only in positive numbers. It does not be negative. Next, this non-negative theory refers to the study of objects. Objects means numbers, functions, matrices, measures, optimization variables, etc. Like that. This power spectral density in the non-negativity theory is mainly study of these objects. And this non-negativity theorem also gives us the that are constrained to be greater than or equal to 0, and to the theorems, structures and algorithms that depend on the property. This is also non-negativity theorem always studies the characteristics of objects, algorithms, structures, theorems, like that. Next, the second property is the power spectral density is always real and even for real signals. For example, if x of j tk is a real valued process, then Sxx of f, it means Sxx of means power spectral density equal to Sxx of minus f. It means when we give the negative frequency, it will gives us the positive frequency. So the PSD is even and real. This is the formula for even functions. When you give the negative numbers in a function, it will always gives us the positive numbers. It is called even. Next, for complex signals, symmetry depends on whether the signal is proper means circularly symmetric. Next, third property is about Fourier transform of the autocorrelation function. Next, Fourier transform of the autocorrelation function means for a WSS process. WSS means wide sense stationary process. The power spectral density of the function is Sxx of f equal to integral minus infinity to infinity Rxx of t into e minus j into 2 pi ft dt. It is Sxx of f means power spectral density. The limits of the autocorrelation function is minus infinity to infinity into energy minus j into 2 pi ft dt. And the inverse of that process is Rxx of j tk. It means the autocorrelation function, that equals to a into minus infinity to infinity integral Sxx of j into f of k e power j 2 pi ft into df. Mainly in this power spectral density, this is also known as the Wiener-Khinchin theorem. Before also we know this, the Wiener-Khinchin theorem. Here this is the formula for the autocorrelation function, Fourier transform of the autocorrelation function. This is also one of the properties of the power spectral density. Next, the fourth property of the power spectral density is, this means the total power equals area under the PSD. The total power of the power spectral density equals to the area under the PSD. It means power equal to Rxx of 0, that equals to integral minus infinity to infinity Sxx of f into df. When we integrate the power spectral density with respect to frequency, we will get the power. The power is also represented by autocorrelation function at 0 instant of time. Next, the integral, it means the inverse, this is also referred to as the integral of the PSD. It means the integral of the power spectral density gives the average power of the process. This Rxx of 0 is also known as average power of the process. This integral minus infinity Sxx of f with respect to frequency is also known as power spectral density. Next, the fifth property is linearity for sums of uncorrelated process. This is this is the main and most important property of the five properties. First, if x j of t of k equals to x x1 j t of k plus x2 j t of k, and the processes are uncorrelated, and will also give us s xx of f of k equal to s x1 x1 j f of k plus x x2 x2 j of k. It means when we take two random processes, it means x1 x2 like that. When we when we when we sum the individuality of the power spectral density, it will give the original power spectral density to you. If you if you separate the if you separate uh, if you take two random variables x1 x2, then when you do the calculations of the power spectral density of the individual x1 and individual x2, when you add both the power spectral density of the x1 and x2, you will get the power spectral density of the main. It means s xx of j of k. Next, this theorem is also used heavily in modeling noise sources in electronics. These five properties are used in first, modeling noise sources in electronics. Next, summing independent vibration or audio signals. Lastly, combining independent wireless channels. This is the applications in signals and systems. Next, the main applications of this power spectral density is, it is widely used in signal processing and communications. Mainly signal processing and communication are based on these power spectral density theorem. It is also one of the subject for that. It is also one of the main theory subject for the signal processing communications like that. And it is also used in some of the engineering branches like electronics and electrical engineering, mechanical and structural engineering, biomedical engineering. These have the one of the theory subject in these branches like electronics, electrical, mechanical, structural, and so many branches. Next, it is also used in practical applications like or daily applications like acoustics and audio, radar, sonar and geophysics, finance and econometrics. Like that, power spectral density is used in many of the applications in our daily life. Like here, we listed some 7 to 8 applications in our seminar topic. Thanking you for giving me this opportunity to tell me a seminar topic about power spectral density from my section. Thanking you.